Now, how do you do search in one of these high fan-out search trees? Well, we'll search for 5 in this example. You do binary search on each node, starting at the root. So the root is a single page. We do binary search in that page to figure out which pointer to follow. And then we just go down to the next level, and we do binary search there again until we get to the leaf level, and we've got ourselves the page in the heap file that contains our record. The complexity of this is big O of log base F, the number of pages in the original file, where F is the fan out of one of these nodes in the tree, of one of these pages in these index files. Now we can do a little bit better here. Simple optimization. We really don't need this leftmost key. We can just drop it and still be able to find everything. Implicitly, everything down the leftmost pointer is stuff that is less than the split key to the right. And we don't really care how much less than once we've navigated the tree. So we can drop these left keys, and that's going to save us space and give us more room on each page for more entries. So to build an index file with this high fan-out search tree, we're going to need to lay it out on disk. And what we're going to do is we're going to put all of these layers of this tree into a single file with the leaf level, the data pages, first. So we're going to have a sequential set of pages for the data pages, followed by the index pages with the root first and then the rest of the tree in some order, say in breadth first search. Okay, so this is going to be our index file. And let's evaluate how we're doing on some design goals with this data structure. So does it support fast sequential scan of the data? Is it as good as a heap file? And the answer here is yes, actually. The data is all contiguous in the front of the file, and so a sequential scan will take us through all the data with no random IOs. So that's great. What about in the index pages? Are they supporting high fan-out? Again, the answer is yes. We're doing a good job. These keys and pointers that we're putting on the index pages are quite small. The pages themselves are 256 kilobytes, so you can get quite a lot of pointers onto each page, which means you do get high fan-out. So that's good. What about supporting insertion? Does it support insertion? Well, maybe not so much, and this is one of the weaknesses of our design so far. We'll look at that in just a minute. I do want to point out before we go on that this data structure has a name. It's called an ISAM, or an Indexed Sequential Access Method, and it was invented at IBM in the 1960s. Let's see what the problem is with insertion. So suppose we're going to insert the value 11 into this tree. So before we insert it, our tree looks like this. And to do the insertion, we're going to search the tree for the location where 11 should go, and we'll find that it's in that rightmost page at the leaf level. And since there's space for it on the page, we'll simply put it in the page. Now it happens that 11 is the biggest value on this page, but if it hadn't have been the biggest value, we would have had to resort the page in memory, just the items on that page, so that they are in order on the page. Now that's all fine because there was space for 11 on that page, but suppose the next thing we wanted to do is insert 12. There's no room for 12 in this page at the leaf level. What are we going to do about that? The ISAM answer is, well, we'll allocate an overflow page. And the end of this ISAM file could grow with overflow pages. And we'll store pointers to the overflow pages in the index pages. So each index page will have to have space for a pointer to its overflow pages. And then the overflow pages themselves might be a linked list of pages in the overflow page region. Okay, so this begins to be a little bit unattractive. In particular, you could imagine starting with an ISAM and then loading values into it. Say with this example, values that just get bigger and bigger. And the overflow page chain, which is a linked list, might take up most of the file. And eventually this degrades into just a linear search, and we're basically back to a heap file with no index. So this overflow page is the Achilles heel of the ISAM, and we're going to need to fix it eventually. So let's recap what we did so far. We designed a data structure, happens to have been already invented. It's called an ISAM. And it has its data entries in a sorted heap file, which is the first part of the file. And it has a high fan-out static tree index after the heap file, which is the second part of the file. This supports fast search via the index and good locality of search of scan, in the heap file. Values that should be sorted together are stored together. But this all depends on the idea that we don't change the file. We don't do lots of insertions and deletions. Insertions, as we know, go into overflow pages, which can create linear chains of data and can make search in the limit be order of n instead of order of log base f of n. As I mentioned, the ISAM is an old-fashioned idea, and what we're going to see next, which are B+ trees, are almost always better. Not always better. There's some corner cases, and we'll come back to that. But ISAM is a good place to start. It's simpler than a B+ tree, but it has many of the same ideas. So the upshot here, don't put ISAMs on your resume, but it's good to know them, and it will be good to know in future how they differ from B+ trees, which we're coming to next.